a quiet archive record. Tonight, we cross into a quieter world, where the dark is safe, and the story is enough. Let the day fade away, and quietly slip into the deep. The simulation idea is simple to say and hard to test. It claims that what we call reality might be the output of a deeper system, like a program running on hardware we cannot see. People love this idea because it feels modern, because it fits the way we build digital worlds, and because it explains why the universe is so mathematical. But even if the idea is wrong, it raises sharp questions about what counts as evidence, what counts as a limit of measurement, and how far science can reach. Tonight, we explore 20 ways we could detect we are in a simulation. Most of what follows is not proof. It is a list of test ideas. Each one has a matching objection, because almost every possible simulation clue also has a non-simulation explanation. 2 rules. First, if a claim can explain every outcome by saying the simulator hid the evidence, it is not a detection method. Second, if a claim cannot point to a specific measurable anomaly, it is not a detection method. When people say simulation, they can mean different things. One meaning is literal. Our universe is computed by another universe, step by step. Another meaning is informational. Reality is ultimately discrete information, and the laws are like rules. This episode focuses on the literal and informational meanings, because those are the ones that can, in principle, be tested. Detection 1. Pixelation at the deepest scale. If space-time is computed, it may be discrete, like a grid. In ordinary life, we do not see pixels in space, but at extreme energies, a minimum length might show up as noise, jitter, or a hard cutoff. Physicists already suspect something like this, but for reasons that do not require simulation. Quantum gravity ideas often imply a minimum length near the Planck scale. A test idea is to look for direction-dependent limits in very high-energy cosmic rays. If space is a lattice, certain directions might be favored, the way a grid favors its axis. The objection is that even if we see a minimum length, it can be a property of nature, not a sign of computation. Detection 2. A maximum information density. There are hints that the amount of information in a region is limited by its surface area, not its volume. This is related to the holographic principle. A simulation could also have memory limits. If there is a hard cap on information, it can feel like a storage bound. The objection is that information bounds can arise from black hole physics without any computer running the world. Detection 3. A maximum update speed. The speed of light is a strict limit on how fast information moves. A simulator might also have a maximum update speed. But again, the speed of light can be explained by space-time geometry. A detection angle is to ask whether there are any tiny delays or discretized steps in time, like a universal frame rate. If time had ticks, then extremely precise clocks might reveal it as noise. The objection is that current experiments have not seen such ticking, and even if they did, it might be quantum structure. Detection 4. Unnatural randomness. Quantum outcomes look random. If a simulation uses a pseudo-random generator, the randomness could have hidden structure. In practice, detecting that would be very hard, because a good generator can pass huge test suites. A more realistic test is to look for correlations where there should be none. If many quantum events share a random seed, faint correlations might appear. The objection is that nature could also have hidden correlations from unknown physics. Detection 5. error correction signatures. In modern physics, people have noticed that some math in gravity resembles error correction codes. In computing, error correction protects information against noise. If space-time behaves like an error-corrected code, that could be a clue that the universe is protecting state information. The objection is that error correction patterns can appear in math because they are useful structures, not because there is a computer. Detection 6. Compression artifacts. A computed world might rely on compression. The laws of physics are a kind of compression, because short equations describe huge behavior. But a deeper test idea is whether the universe sometimes trades detail for efficiency, the way lossy compression trades detail for size. What would that look like? One idea is to look for limits in the complexity of quantum states that can be realized. If some states are too complex to compute, the universe might avoid them. The objection is that complexity limits can exist because of energy limits, not because of computation limits. Detection 7. Render on demand. In games, details are generated when needed. A simulation might only compute high detail where an observer is measuring. A test idea is to create experimental setups that demand huge detail in distant or unobserved systems and see if any limits appear. The problem is that physics has been tested at large scales and continues to work. The objection is also that quantum measurement effects already depend on observation, but that does not mean there is a renderer. It can mean the world is quantum. Detection 8. Boundary behavior at extreme observation. If there is a hard cap to how much can be known, then pushing measurement precision might show sudden walls, not just gradual uncertainty, but abrupt limits. Examples might be absolute limits in measuring position, time, or energy beyond what standard quantum mechanics predicts. The objection is that fundamental limits are expected in many non-simulation theories. Detection 9. Physics constants that look tuned for computability. Some constants might not just allow life, but allow stable computation. For example, if the universe had too much chaos or too much noise, stable memory might be impossible. A simulation might choose constants that support stable structures. The objection is that stable structures are also needed for any kind of complex matter, simulated or not. Detection 10. Anisotropy in the vacuum. If the universe is computed on an underlying substrate, the vacuum might not be perfectly symmetric. There might be tiny preferred directions. People already test this with precision experiments, searching for Lorentz symmetry violations. If a violation is found, some might say it is a simulation artifact. The objection is that symmetry breaking can come from new physics. Detection 11. Energy as an accounting system. Landauer's principle links information erasure to energy cost. In computing, information processing has thermodynamic costs. A simulation might still obey an energy budget that looks like an accounting system. The objection is that Landauer applies to computers inside physics, not necessarily to physics itself. Detection 12. Limits on computation inside the universe. If the universe is a simulation, the simulator may not allow inside observers to build devices that crack the system. A test idea is to explore whether there are hard limits on building hypercomputers, machines that would compute beyond what physics allows. The objection is that physics already seems to forbid hypercomputation for deep reasons. Detection 13. Strange regularities in high complexity systems. A simulation might smooth or regularize extremely complex behavior to keep it tractable. One place to look is turbulent fluids and chaotic systems. Does nature ever cap chaos in a way that looks like numerical stability? The objection is that turbulence is already hard and our models are incomplete. Detection 14. A tell in the cosmic background. If a simulation had an initial condition, it might have a signature like a watermark. Not text, but a pattern. One candidate is the cosmic microwave background, the oldest light we can measure. People already search it for anomalies and patterns. The objection is that anomalies can come from inflation, systematics, or chance. Detection 15. Quantum non-locality as an optimization. Entanglement links distant particles. It looks like information is not local in the way we expect. A simulation might use non-local shortcuts to reduce computation. But entanglement does not let you send messages faster than light, so it is not a simple cheat. The objection is that entanglement is a core feature of quantum theory. Detection 16. Glitch-like failures under extreme load. If a simulation has resource limits, then in rare extreme conditions, it might fail, like a numerical instability. A place to look would be near black holes or during ultra-high energy collisions. The objection is that extreme conditions produce extreme physics, and we should not call unknown physics a glitch. Detection 17. Evidence of discretized time. If time advances in steps, then ultra-stable clocks might reveal a noise floor. People are building clocks that can detect tiny variations in fundamental constants. If a universal tick exists, it could show up as a line in frequency space. The objection is that quantum fluctuations already create noise. Detection 18. The possibility of a hidden interface. In a simulated system, there might be an interface layer. If there is, it could leak through in ways that look like constraints on what can be observed. This is similar to the idea that measurement is like querying an API. A detection attempt might look for patterns in measurement outcomes that depend on experimental design in a way that goes beyond quantum contextuality. The objection is that quantum contextuality already tells us outcomes depend on the measurement context. Detection 19. The nested simulation argument as a probability clue. If civilizations can create simulations, then there could be many simulated worlds. Some philosophers argue that this raises the probability that we are in one. This is not a test. It is a prior. The objection is that we do not know if simulations of conscious beings are possible, or ethical, or common. Detection 20. Cross-checking consistency across scales. A simulation might use different approximations at different scales. If so, there could be tiny inconsistencies between the laws as inferred from particle physics and the laws as inferred from cosmology. Scientists already look for this in the tension between measurements of the Hubble constant, dark matter models, and other parameters. The objection is that tensions are common in science and often resolve with better data. Before we step back, it helps to slow down and walk through the 20 ways in a more documentary rhythm, with more detail about what each test would actually look like. Way 1, pixelation at the deepest scale, is often imagined like a screen, but the more realistic version is not a visible grid. It would be a subtle change in the math of motion at extreme energies. If space is continuous, then in principle, you can rotate a system by any angle, and nothing fundamental changes. If space is a lattice, then rotation symmetry is not perfect. Most angles would be approximations. At low energy, the difference might be invisible. At extremely high energies, the difference might leak out. So what would you look for? One target is the highest energy particles that hit Earth, the ultra-high energy cosmic rays. These are particles with energies so large that a single proton can carry the energy of a thrown baseball compressed into one particle. When they slam into the atmosphere, they create huge showers of secondary particles. There is also a known feature called the GZK cutoff, named after Greisen, Zatsepin, and Kuzmin. It predicts that beyond a certain energy, cosmic rays lose energy by interacting with the cosmic microwave background. In other words, the universe itself becomes a fog that slows them. If the rules of motion were slightly different because of a lattice, the shape of that cutoff might shift. Some energies might be allowed that should not be, or some directions might show a different cutoff. That is why the anisotropy idea matters. The non-simulation explanation is always nearby. Even if you saw an anisotropy, it might mean cosmic rays come from a nearby region of the sky, or it might mean magnetic fields in intergalactic space guide them, or it might mean we are seeing heavier nuclei rather than protons. So a simulation claim would require a pattern that matches a lattice calculation, not just a bump. Way 2, a maximum information density, is linked to one of the strangest facts in physics. Black holes behave like thermodynamic objects. They have entropy, they have temperature, and the entropy scales with surface area. Entropy is a measure of microstates. In simple terms, it counts how many different internal configurations could look the same from the outside. For an ordinary box of gas, entropy scales with volume. For a black hole, it scales with area. If you were a programmer, you might say the area scaling feels like a storage rule, like the system stores information on the boundary. But a physicist can say something deeper. It could mean space-time itself is not fundamental. The degrees of freedom might live on a lower dimensional boundary. This is the core of holographic thinking. If space-time is emergent from information, that is not the same as being simulated, but it is a world where information is primary. A detection angle might be to find more direct evidence that space-time emerges from entanglement structure. This is an active area of research. It does not take the form of one simple experiment. It is a long program. Way 3, a maximum update speed, is often framed as a universal refresh rate. But the speed of light is not a refresh rate. It is a causal structure. Still, you can ask whether there is a smallest time interval that has meaning. Some theories of quantum gravity suggest something like that. If time was discrete, then extremely precise timing experiments might see it as a jitter flaw, like a graininess in time. Modern experiments use optical frequency combs, stabilized lasers, and atomic transitions. They can compare time to absurd precision. If there were a strict tick, it might show up as a resonance, a periodic artifact that refuses to average away. But the objection is heavy. Even if such an artifact were found, it could be a feature of quantum gravity. Also, a simulation does not need a tick. Way 4, unnatural randomness, is a tempting idea because pseudo-randomness is common. But we should be careful. There is a difference between randomness in the outcomes and randomness in the settings. In Bell tests, researchers choose measurement settings randomly so that any hidden coordination is unlikely. They have even used distant starlight to generate the random choices, So the choice is influenced by photons that left stars centuries ago. These tests are designed to close loopholes in local hidden variable models. If you wanted a simulation test, you might ask a strange question. Do the random settings and the random outcomes show correlations that should not exist? The problem is that if the universe is quantum, correlations exist, but in a known structure. So you would have to look for extra correlations beyond quantum predictions. That requires huge datasets and very careful analysis. Way 5, error correction signatures, is one of the most serious modern links between computation and physics. In quantum computing, error correction is essential because quantum states are fragile. In modern theoretical physics, especially in holography, people have found that the mapping between a boundary theory and a bulk gravitational theory can behave like an error-correcting code. This does not mean a simulator wrote an error correction layer. It could mean that the math of consistent physical theories naturally has error correction-like structure. But if the universe has a built-in mechanism that protects information in a way that looks like engineered redundancy, then it is a clue that information is central. Way 6, compression artifacts can be misunderstood. The laws of physics being simple is not a compression artifact. It is a feature of lawful reality. A better version of the test is to ask whether the universe forbids certain high-complexity states, not for energy reasons, but for algorithmic reasons. For example, some people talk about the complexity of describing a quantum state. A general quantum state of many particles takes an enormous amount of information to write down. Yet nature seems to realize such states without trouble. So any compression claim must be subtle. It might appear as a limit on entanglement complexity, or a limit on circuit depth, or a limit on the growth of computational complexity in certain systems. These are not easy tests. They are more like research programs. Way 7, render on demand, is the classic video game analogy. If reality was computed lazily, then unobserved details would not exist until measured. But quantum theory already contains a limit. You cannot assign definite values to all properties at once. So many people confuse quantum indeterminacy with lazy rendering. A real lazy renderer would likely create artifacts, missing detail, inconsistent histories, or computational shortcuts. One thought experiment is to set up systems where many observers independently measure the same distant system at different times, then compare notes for consistency. In practice, physics already predicts consistency through entanglement and decoherence. So again, you would need a deviation. Way 8, boundary behavior at extreme observation, is close to a general idea in physics. There may be ultimate limits. Heisenberg uncertainty is one kind. Black hole formation, when you concentrate too much energy, is another. If you try to measure too precisely, you may collapse the region into a black hole. That is not a simulation clue. It is just physics. But a simulation clue would be if those limits had an extra feature, like an arbitrary cutoff at a scale that does not fit any theory. Way 9, constants tuned for computability, is a subtle argument. In any world with chemistry, you need stable atoms. You need stable stars. You need long-lived structures. These constraints also support computation. So it can look like the universe is tuned for computation, even if it is just tuned for complexity. If you wanted to sharpen this, you could ask whether the constants also optimize something like computational efficiency, not just stability. That is hard to define. Way 10, anisotropy in the vacuum, is a real experimental question. Physicists test Lorentz invariants constantly. If the vacuum had a preferred direction, then the behavior of particles could depend on orientation or speed relative to that direction. This would be revolutionary, and it would also be immediately claimed by some as simulation evidence. But the honest view is that it would most likely be new physics. The simulation interpretation would be optional. Way 11, energy as accounting, often uses Landauer's principle. Landauer says that erasing one bit of information costs at least kT-ln2 energy as heat. This ties information to thermodynamics, but it does not say that the universe is a computer. It says that computers are physical. Still, if you find deep links between information and energy, it supports the idea that information is not just a human description. Way 12, limits on computation inside the universe, is a place where science already has answers. For example, you cannot build a machine that computes faster than light allows signals to travel. You cannot store infinite information in finite space. You cannot run an infinite number of steps in finite time, at least not in ordinary physics. These are not simulation censorship. They are physical constraints. But if you found an extra constraint that seems designed to prevent certain experiments, that would be strange. Way 13, strange regularities in high complexity systems, is where the word numerical can appear. When we simulate fluids, we see numerical viscosity, artificial diffusion caused by finite resolution. If the universe was computed with finite resolution, would it show artificial diffusion? This is hard because real fluids already have viscosity and turbulence. So again, you would need a clear mismatch between theory and observation. Way 14, a tell in the cosmic background, is often a fantasy of a message. But if you think like a scientist, you can frame it as an anomaly search. The cosmic microwave background has small temperature fluctuations. These fluctuations are described by an angular power spectrum. If the initial conditions of the universe had an unusual pattern, it could show up as a feature in that spectrum. People already search for non-Gaussianity, hemispherical asymmetry, and unusual alignments. So far, nothing demands a simulation explanation. Way 15, quantum non-locality as optimization, is more of a metaphor. Entanglement is non-local in correlation, but not in signal. It does not let the universe cheat causality, but it does show that information is not stored locally in the naive way. If space-time is emergent, entanglement may be the glue. Way 16, glitch-like failures under extreme load, is the most cinematic idea. People imagine reality stuttering, but real science would look for breakdowns of known laws at extreme conditions. The closest we have are places where our theories conflict, singularities in general relativity, and the need for quantum gravity. If a simulation existed, those conflict zones might be where artifacts appear, but they might also be where deeper physics lives. Way 17, evidence of discretized time, overlaps with the clock idea. It also overlaps with searches for tiny violations of energy conservation or changes in particle behavior. A discrete time step could, in some models, break certain symmetries. People search for these effects. Way 18, a hidden interface, is another metaphor. In computing, an interface is a limited set of allowed interactions. In physics, measurement is always interaction. The question is whether the set of interactions is limited in a way that looks designed to hide a deeper layer. Quantum contextuality already shows that outcomes depend on measurement context. Some people might reframe that as an interface, but that does not add evidence. Way 19, nested simulation probability, is a different kind of argument. It does not look for evidence. It looks at a space of possibilities. Bostrom's argument, in simplified form, says that if many advanced civilizations run many simulations, then simulated observers could vastly outnumber base observers. If you assume you are a random observer, you might then think you are likely simulated. The criticism is that the assumptions are unknown. Maybe advanced civilizations do not run many simulations. Maybe consciousness cannot be simulated. Maybe ethical rules prevent it. Maybe the resources are too large. So it remains a philosophical point, not a detection method. Way 20, cross-checking consistency across scales, is the kind of thing real science does all the time. Physics is a network of constraints. Particle physics, cosmology, and astrophysics should agree. When they do not, it could mean missing physics. Some people might say it could mean a simulation using approximations at different scales. That is possible as a story, but again, the default explanation is that our models are incomplete. There is also a deeper practical issue that sits behind many of these tests. A simulation hypothesis can copy any physical law you like. If the simulator wants the inside world to look like quantum field theory plus general relativity, then they can implement those rules. If they want it to look like something else, they can implement that. So the only reason we expect artifacts is because of cost. Computation costs resources. Storage costs resources. Perfect accuracy costs resources. If a simulated universe is cheap, then the edges might show. If it is expensive, the edges may never show to the inside observers. That is why some detection strategies focus on stress tests. Not stress in an emotional sense, but stress in a resource sense. You design an experiment that, if computed naively, would require huge resources. Then you see if nature behaves as if it is paying that cost. This is where ideas from computational complexity enter. There is a concept called computational irreducibility, often associated with Stephen Wolfram. The idea is that some processes cannot be shortcut. You have to run them step by step. If the universe is running processes step by step, then the universe is doing computation, simulated or not. But if the universe is simulated, the host world might try to shortcut. A shortcut could look like a loss of detail or a statistical approximation. The hard part is that we already see statistical approximations in physics, but those are not shortcuts. They are fundamental. So again, the test must be precise. One concrete direction people discuss is the growth of complexity in quantum systems. In some theoretical work, complexity grows for a long time and is linked to concepts like black hole interiors. If complexity is physical, then the universe might have a maximum complexity bound. A simulation might impose such a bound, but even a non-simulated universe might impose it. So the more honest framing is that simulation detection blends into quantum gravity. Another practical direction is to look for signs of finite precision. Computers use finite precision numbers. Physics often uses continuous quantities. If the universe used finite precision, then conservation laws might fail at tiny levels. For example, energy might not be conserved perfectly in every event. Momentum might show tiny quantization. Phase relationships might drift. people already test conservation laws to extreme precision. So far, they hold. But if any systematic drift were found, it would be significant. Not a simulation proof, but a major clue that our math is incomplete. Another detection route is to think about limits on observation itself. The universe may hide its deepest layer, simulated or not. For example, if quantum gravity prevents observation beyond certain scales, then the bottom layer might be unreachable. In that case, simulation becomes a metaphysical claim, not testable. So what would count as strong evidence? It helps to imagine the day it happens. A research group runs an experiment for years. They swap equipment, they change labs, they invite skeptics, they publish methods, they repeat the run, and the anomaly stays. It is not one strange data point. It is a stable deviation. It is a rule that nature seems to follow. At first, it is small. It sits inside the error bars. Then the instruments improve. The error bars shrink. The deviation remains. Then other groups see it. Then a theory appears that explains it as new physics. And then, only after that, someone says a sentence that sounds like science fiction. What if this looks like a computational artifact? That is how the simulation idea would enter science in a serious way. Not as a first explanation, but as a last explanation after we have exhausted normal mechanisms. Even then, it would not be proven. It would be argued, and it would be argued in public, with data. So the best way to keep the topic grounded is to set that standard. If a claim does not point to a specific, measurable anomaly, it is not a detection method. If a claim survives every outcome by saying the simulator hid it, it is not a detection method. If a claim relies on personal feelings, it is not a detection method. A strong piece of evidence would have three features. First, it would be robust across instruments. Second, it would be specific, not vague. Third, it would be easier to explain as an engineered artifact than as a natural mechanism. For example, imagine a repeated pattern in high-energy particle collisions that matches a lattice dispersion relation exactly, with the same orientation across different labs and different machines. That would be strange. Or imagine a frequency comb in the noise of the best atomic clocks, with a spacing that is constant across different clock designs, different countries, and different gravitational potentials. That would be strange. Or imagine that in a certain class of quantum experiments, a particular sequence of outcomes repeats with a probability that is impossible under quantum theory, but consistent under a pseudo-random generator with a short seed. That would be strange. Each of these examples is not a proof by itself, but it would justify serious attention. Now, there is another reason people like the simulation idea. It gives a story to the feeling that reality is filtered. In everyday life, you never perceive all detail. The brain compresses. It selects. So the mind already lives in a kind of model. This is not simulation as physics. This is simulation as perception. The danger is to mix the two. A person can feel that reality is a model and then conclude that physics is a program. That jump is not justified, but it does explain the emotional grip of the idea. When people talk about the Matrix, they are often describing a sense that the world is thin, that the rules are strange, that the self is trapped in a system. The simulation hypothesis turns that feeling into a claim about the universe. Science has to keep those separate. Now, we can return to the 20 ways as a single, simple takeaway. If you want to detect simulation, you look for limits. You look for symmetry breaks. You look for correlations. You look for discretization. You look for resource boundaries. But you also accept that a good simulation can hide. And you accept that many simulation-like signatures are also just deep physics. There is also a simple way to group the 20 methods, which can make them easier to remember. Group 1 is geometry tests. These are tests that look for the shape of space-time itself, discrete space, discrete time, preferred directions, and altered dispersion relations. If you want a mental image, imagine walking on a tiled floor in the dark. If the tiles are large and your steps are small, you may never notice the grid. If you sprint and jump, you might feel the seams. In physics, sprinting and jumping means pushing energy higher, pushing distances smaller, and pushing timing tighter. This is why high-energy particle accelerators matter. The Large Hadron Collider is not a simulation detector. It is a microscope. It smashes particles to reveal what they are made of. But if space-time had a discrete structure, then at some scale, the behavior of particles could deviate from the continuous equations. It might show up as unexpected scattering patterns. It might show up as a cutoff, where certain interactions stop behaving smoothly. It might show up as tiny violations of expected symmetries. So the simulation question is not separate from particle physics. It is a dramatic framing of the same search. The same is true for astrophysics. Nature accelerates particles far beyond what we can do in a lab. So we watch the sky. We watch for ultra-high energy cosmic rays. We watch for gamma rays. We watch for neutrinos. We watch for gravitational waves. If any of these messengers shows a systematic deviation from expected behavior, the first story will be new physics. The second story, for some people, will be simulation. But the data comes first. Cosmic ray anisotropy fits here. So do precision tests of Lorentz invariance. So do experiments that compare how particles behave at different velocities and orientations. In real laboratories, one example style is to trap atoms or ions and measure transition frequencies as the Earth rotates. If there is a preferred direction in space, the frequency could drift with the lab's orientation. These are not science fiction experiments. Variations of them exist. Group 2 is information tests. These are tests that treat the universe like an information system. Holographic bounds, error correction, computational complexity, and limits on state preparation. This is where modern theory is active. If space-time is emergent from entanglement, then entanglement is not just a feature of particles. It is a feature of geometry. That turns simulation into a question of what the universe is made of. Group 3 is noise and randomness tests. These are tests that look for patterns in things we expect to be patternless. Quantum randomness, clock noise, background fluctuations. If there is a machine, noise can have fingerprints, but noise can also be natural. So the test is not just to find noise, it is to find the wrong kind. Group 4 is stress tests. These are tests that attempt to push nature into high resource demand, large entangled states, high energy collisions, extreme astrophysical systems, black hole environments. The weakness is that we cannot easily access the extremes. Most of the universe is out of reach, so we use cosmic messengers, photons, neutrinos, and gravitational waves. In recent years, detectors like LIGO and Virgo have measured gravitational waves from merging black holes and neutron stars. These events test gravity in regimes we cannot produce in the lab. If gravity had a discretized structure, or if it violated known symmetries, these signals might show it. So far, general relativity keeps surviving, but the detectors improve, and as they do, they constrain more models. They also give us a different kind of stress test. If space-time is computed, then violent events might reveal numerical-like behavior. Not cartoon glitches, but tiny biases. For example, the waveform from a merger has a precise shape. The inspiral phase is predictable. The ring-down phase depends on the final black hole's modes. If the underlying structure of space-time had a discrete scale, it might slightly alter those modes. If gravity leaked into extra dimensions, it might alter them. If the speed of gravity depended on frequency, it might alter them. These are not simulation-specific predictions. They are general new physics predictions, but they show why simulation detection often collapses into a search for new physics. The same data that could constrain a simulator also constrains quantum gravity. In the same way, neutrino astronomy can test deep physics. Neutrinos pass through matter. They carry information from dense regions. If particle behavior changes at extreme energies, neutrinos might reveal it. So when you ask how we could detect a simulation, one answer is simple. Keep building detectors. Keep pushing precision. Because if there is a bottom layer, we will only find hints of it at the edges. Now we can add one more layer of detail to several specific ways. Consider the idea of a preferred direction. If space-time has a lattice, the lattice has axes. If it has axes, then the universe is not exactly the same in every direction. Physicists call this violation of isotropy. One reason this is appealing as a simulation clue is that most deep physical theories lean towards symmetry. A lattice breaks symmetry, but symmetry breaking can also happen in nature. Crystals break symmetry. The vacuum might break symmetry. So the detection question becomes, do we see symmetry breaking in fundamental laws, not just in materials? Now consider the idea of a hard maximum energy or a hard maximum momentum. Some theories propose a maximum energy scale. Others propose modified dispersion relations, where the relation between energy and momentum changes at extreme energies. If this were true, then very high energy photons from distant sources might arrive at slightly different times depending on energy, even if emitted at the same moment. People have looked for this in gamma ray bursts. The idea is that if light speed depends on energy, then high energy photons might lag or lead. The results so far do not show a clear effect. If an effect were found, it would be a sign of quantum gravity or new physics. And again, simulation would be one interpretation. Now consider the idea of a watermark. A literal message in the cosmic microwave background is unlikely, but a subtle engineered constraint could be more realistic. For example, if a simulator wanted to prevent certain forms of measurement, they might impose a rule that looks like a law. If that law had an arbitrary cutoff, it could be suspicious. But we have to be cautious. The universe already has arbitrary-looking numbers, like the value of the fine structure constant. We do not know why it has that value. Calling unknown constants a watermark is not scientific. Now consider the idea of render on demand and observation. The simulation idea often mixes with the idea that consciousness collapses the wave function. That claim is not required by quantum mechanics. Most working physicists treat measurement as physical interaction, not as mind. So a detection method should not depend on consciousness. If there is render on demand, it would have to depend on measurement, not belief. That makes it testable. But again, quantum theory already depends on measurement context. So any simulation renderer would have to differ from quantum theory. Now consider a final important point about loops and consistency. If a simulator wanted to keep the world stable, they would enforce consistency. They would prevent paradoxes. They would prevent inside observers from sending information backward in time. They would prevent experiments that crash causality. The fact that physics seems to protect causality could be interpreted as design, but it can also be interpreted as structure. The universe might simply be the kind of object that cannot contain contradictions. After all this, we can step back. Now we step back. There is one more thing worth adding, because it changes how you hear the whole list. Most proposed simulation tests quietly assume that the simulator is optimizing for efficiency. That is a human assumption. It comes from our own constraints. We live on limited hardware. We pay for electricity. We wait for renders. We compress files. So we imagine that any simulated universe must also be optimized. But that might be wrong. A simulator could be unimaginably rich. They could waste resources the way we waste air. If that is true, then artifact hunting becomes a weak strategy, because the simulation could run with extravagant redundancy and precision. In that case, the only possible evidence would be evidence of intention, not a bug, not a limit, but a choice. For example, a law that looks unnecessary but is enforced anyway, or a set of constants that fall into a pattern that looks designed, or a boundary condition that looks like a rule written by an author. The problem is that humans are pattern seekers. We can see intention in almost anything if we stare at it long enough. So even intention is a dangerous kind of evidence. Still, we can ask what intention would look like in physics. One possibility would be a rule that is simple, stable, and seems to exist only to make the universe consistent for observers. Another possibility would be a deep connection between information, observation, and law, where the universe behaves like it is protecting a consistent narrative. This may sound mystical, but there is a clean scientific version. Science depends on repeatability. Repeatability depends on the universe behaving the same way tomorrow. If the universe were allowed to change rules freely, science would fail. So any universe that contains scientists must have stable rules. That is not design, it is selection. Only stable rule worlds produce observers who can ask. This is a form of observer selection effect. It is similar to how life-friendly constants can be explained without direct design. Now consider a different angle that is often ignored. If we are in a simulation, it might not be a simulation of physics. It might be a simulation of minds. The physics could be a scaffold designed to generate certain experiences. If so, the best tests might not be found in particle accelerators. They might be found in the structure of perception and cognition. For example, you could ask whether human perception has built-in limits that feel like interface limits. We cannot see most wavelengths. We cannot hear most frequencies. We experience time in a narrow way. We build a world model that is useful, not complete. Again, this is not proof. It is just an observation. But it matters because many people take the simulation idea seriously because of how perception already works. So if you want to keep the discussion grounded, you can say this. Even if the universe is not simulated, our access to it is. We live inside a model built by the brain. And because of that, we will always be tempted to confuse the limits of the model with the limits of reality. This is why the best detection ideas are always the ones tied to instruments, not to feelings. One more practical point. Even when we think we are doing pure physics, we are doing inference. We never observe the whole universe. We observe traces. A detector clicks. A telescope collects photons. A spectrum shows lines. A wave pattern appears on a screen. Then we build a model that best explains those traces. This matters because a simulation, by definition, can control the traces. It can give you the same trace distribution as an unsimulated universe. So in a strict sense, if a simulation perfectly imitates a non-simulated world, you cannot tell. That is not a defeat. It is just a limit. In the same way, if you are reading a perfect novel, you cannot prove it is fiction from inside the story, because the story contains only what the author provides. So any detection program depends on the simulation being imperfect, or on the simulator allowing leakage. That brings us to motive. Why would a simulator allow detection? There are several possibilities. They might not care. They might not expect us to get this far. They might allow it as part of the experiment. Or detection might be impossible, and we are chasing a mirage. This is why the simulation question can slide into philosophy. But science can still operate inside that uncertainty. Science can still do what it always does: measure, compare, constrain. And when two explanations fit the data, prefer the one that adds fewer assumptions. In most cases, new physics will be a better explanation than an external simulator. But if new physics begins to look like computation, like discrete structure, like information bounds, then the simulation story will keep returning. Not because it is proven, because it keeps matching the shape of what we find. Now, with that caution in place, the list becomes clearer. If you listen to this list, you may notice a pattern. Almost every detection path depends on the same kind of move. Push measurement to extremes. Look for hard limits. Look for preferred directions. Look for hidden correlations. Look for signs of information processing. And then, when you find something, do not jump to simulation. First ask if known physics can explain it. Because a simulation is not a normal scientific theory. It is a container that can hold many different mechanisms. One simulator might compute space-time on a grid. Another might compute it with a continuous model. One might enforce a hard frame rate. Another might use event-driven updates. One might render on demand. Another might compute everything at full detail. So the best way to make progress is to treat simulation as a family of models, then ask what specific models would predict. We can sharpen several of the 20 ways by adding more concrete details. Take the lattice idea. In 2012, a physicist named Silas Bean, with colleagues Zohre Davoudi and Martin Savage, published a paper exploring what a cubic space-time lattice might imply for ultra-high energy cosmic rays. The argument was not that we are simulated. The argument was that if space-time had a lattice structure, it could break rotational symmetry at extreme energy scales. In that case, cosmic rays might show a preferred direction pattern, or a change in the expected cutoff energy. This is the kind of clue that is at least measurable in principle. Cosmic rays at the highest energies are rare, but they do exist, and large detectors watch for them. The Pierre Auger Observatory in Argentina and the Telescope Array in Utah are two well-known efforts in this space. They do not search for simulation evidence as their main goal. They search for astrophysical sources and basic physics. But the same data could constrain lattice-like models. The weakness is that cosmic ray propagation is messy. Magnetic fields bend paths. Sources are uncertain. A strange pattern might come from nearby galaxies or unknown accelerators. Still, if a lattice signature existed, it would likely show up as a very specific kind of anisotropy. Now take the idea of discretized time. If time had a universal tick, then extremely stable clocks could, in principle, detect a noise floor that cannot be averaged away. Atomic clocks already reach unbelievable precision. Optical lattice clocks can measure tiny differences in gravitational potential across a room. Scientists use these clocks to test whether fundamental constants drift. They test whether the fine structure constant changes. They compare clocks based on different atoms. They look for signals that could come from dark matter fields. A simulation tick would be hard to isolate because many noise sources exist, but if there was a strict periodic artifact, it could show up as a line or comb in frequency space. The objection is strong. There are many reasons for noise. A tick is not required by computation either. A simulator could compute events without fixed time steps. Now take the idea of render on demand. This is popular because it mirrors video games. But physics is not a game engine. If the universe was rendered only when observed, then experiments that delay measurement choice might reveal strange behavior. Quantum physics already has delayed choice experiments. In some setups, it is possible to decide which property to measure after a particle has already entered the apparatus. The results match quantum theory. They do not show a simple renderer deciding late, but there is still a detection-style question hidden here. Is there any experiment that forces the world to commit to a huge amount of detail without giving it a chance to hide behind uncertainty? One proposed direction is to create complex, entangled states with many particles, pushing towards states that are hard to simulate even on powerful computers. The thought is that if the universe is computed, then beyond some complexity threshold, it might fail, or it might take shortcuts. The honest problem is that the universe is not a computer inside itself. It is the substrate. The complexity that is hard for our computers might be easy for nature, but the idea of complexity thresholds remains interesting. In the last decade, researchers in quantum computing have used the term quantum advantage to describe tasks that are hard for classical simulation. If those tasks become routine in the lab, then it would be strange to claim that the universe itself cannot handle them. So if you want a crisp version of the test, it is not that nature fails at complexity. It is that nature might show limits that line up with specific computational resource bounds. Now take the randomness idea. People often say a simulation would use pseudo-randomness, but a simulator could also use real randomness, or could sample from a quantum source in the host world. So finding pseudo-random structure would not be guaranteed. But there is still a test question. Do quantum outcomes pass all statistical tests expected of true randomness? Experiments have already done massive tests of Bell inequality violations using random measurement settings, sometimes using astronomical sources to choose settings, to reduce any possibility of hidden coordination. These experiments do not prove simulation or non-simulation. They test local hidden variable theories. Still, the more you trust quantum randomness, the less you expect a cheap pseudo-random generator. So the practical path here is not to look for simple patterns. It is to treat randomness as a measurement tool, not a clue. Now take the information-bound idea. The holographic principle suggests that a region's information content might scale with its boundary area. This is deeply tied to black hole entropy. If you wanted a simulation angle, you could say this looks like a memory optimization. Store the bulk information on the boundary. But that is not the best framing. The best framing is that physics may be telling us that space-time itself is emergent from information. If space-time is emergent, the simulation idea becomes less special. Reality would already be a kind of computation-like structure, without requiring an external computer. This is where the simulation debate often shifts. Some people start with the thought that the universe is like a computer. Other people start with the thought that the universe is made of math. The philosopher Nick Bostrom is famous for arguing that if advanced civilizations run many ancestor simulations, then it may be more likely that we are in one. But there is a different line of thought from physicists like Max Tegmark, who argue that the universe is a mathematical structure. These are different claims. Bostrom's argument is probabilistic and depends on assumptions about future technology and behavior. Tegmark's idea is metaphysical, that math is not just a description, but the substance. Neither gives a direct lab test. So we return to tests. A useful way to think is to ask what a simulator would have to hide. If you want to simulate a universe, you want to prevent the simulated observers from finding the hardware. You want to prevent them from sending messages outside. You want to prevent them from measuring the update cycle. You want to prevent them from forcing the simulation to reveal resource limits. That suggests several classes of constraints. One class is speed limits. Another is information limits. Another is measurement limits. Another is censorship of certain experiments. The trouble is that all of these also exist as normal physics constraints. So the best simulation evidence would be something that is hard to explain as natural law. What could that be? One candidate would be a literal watermark, a pattern that looks like an intentional message. People have proposed looking for patterns in the cosmic microwave background that could encode information. The problem is that this can become a Rorschach test. With enough searching, you can find patterns in noise. A better version would require a pattern with a low probability under any known physical process, and that is robust across instruments. Another candidate would be a hard computational failure. For example, imagine that for certain experiments, the universe refuses to produce a result or produces obvious numerical artifacts. But we have never seen anything like that. And if a simulator was competent, they would avoid it. So where does that leave us? It leaves us with a realistic expectation. If simulation is true, it might not be detectable, but the search can still do something valuable. It forces us to ask what is fundamental. Is space-time fundamental? Is information fundamental? Is the wave function fundamental? Are laws fundamental? Or are these emergent from something deeper? When physicists talk about quantum gravity, they are already asking questions that rhyme with simulation. And when engineers build virtual worlds, they are building systems that show the same kinds of limits: finite resolution, finite update speed, finite storage. So the simulation idea is not only about the universe, it is also about us. It is about what kinds of worlds we might create. And it is about what kinds of beings might live in those worlds. Now we can give a clean ending. We may never be able to prove we are simulated, because a good simulation could hide the evidence, and because many simulation-like signatures overlap with normal physics. But we can still build sharper tests. We can still push precision. We can still check symmetries. We can still measure noise floors. We can still explore complexity. And if we ever find a result that looks like a genuine artifact, something that does not fit any natural mechanism, then the simulation question would stop being a late-night thought experiment. It would become a real scientific problem. And if that ever happens, the scientific response would be slow and strict. It would be replication first, independent instruments, independent teams, then theory work that tries to explain the anomaly with the smallest change to known physics. Only after that would the larger stories matter, because science does not run on wonder. It runs on constraints. A single clean constraint can kill a whole family of ideas. A single clean anomaly can open a new chapter. So the simulation question, if it ever becomes real, will not be settled by a viral video or a clever argument. It will be settled by years of careful measurements, boring meetings, error budgets, and repeated tests. There is a final irony. The better our science gets, the more the universe begins to look like information. We describe particles as excitations of fields. We describe measurement outcomes as probabilities. We describe black holes in terms of entropy and bits. We build quantum computers where the basic unit is not a switch but a state. None of this proves simulation, but it does mean that the simulation metaphor keeps getting stronger as a way to talk about what we find. It is possible that the metaphor is only a metaphor. It is also possible that the metaphor points to a deeper truth, that reality is built from something closer to information than to matter. In that case, whether or not there is an external computer, the universe would still share the same logic as computation, limits, codes, and structure. Until then, the most honest position is to treat the simulation idea as a map of curiosity, not a conclusion. And if you ever find yourself staring at the sky and wondering, the best next step is always the same. Measure what you can, doubt what you cannot, and keep going, one test at a time. This was a quiet archive story, where the story ends, sleep begins,